Hi, I'm Melissa Hartwig, and today I'm going to be talking to you about the total differential, which comes to us from chapter 13.4. I've started with the basic definition of the total differential, which is that if w is a function of x, y, and z, then the derivative of w is equal to the derivative of w with respect to x times dx plus the derivative of w with respect to y times dy plus the derivative of w with respect to z dz, with dx equals the change in x, dy the change in y, and dz the change in z. So the problem I'm going to be doing with you for this is problem number 9 from this section, and that is a function w equals 2z cubed y sine of x. So first thing that we're going to need to do is differentiate this function with respect to its individual variables, as shown above. So dw with respect to x is going to be, as all of these are constants in front of the sign, 2z cubed y, and then of course the derivative of sine of x is cosine of x, and then this entire thing is multiplied by dx. Then we're going to need to differentiate w with respect to y. Now, the 2 and the z and the sine are all constants for this function, so they'll stay the same. And y, of course, its derivative is going to be 1, so it's just going to go away. So we will have 2z cubed sine of x dy. Now, to differentiate with respect to z, dw of z, we're going to bring the 3 over. The 2 becomes a 6. Z cubed becomes z squared. Y stays the same. Sine of x stays the same, and then this gets a dz at the end. Now, as shown up in the definition, we're going to combine these three things into the total differential of dw, so that we will say that dw is equal to 2z cubed y cosine of x dx plus 2z cubed sine of x dy plus 6z squared y sine of x dz. And that is how you find the total differential of a function through its differentiated variables. Okay, so now the next thing that I am going to talk to you about today is going to be using the differential that you come up with for the total differential to help estimate a value. So we're going to start with number 13 from this section, which is a function f of xy is equal to 16x squared, 16 minus x squared minus y squared. Okay, and it wants us to do this for the points f of 2, 1 and f of 2.1, 1.05. Okay, so those are the points that we're going to work with. So the very first thing that we are going to do is evaluate our function at these 2 points. So we're going to have f of 2, 1 is going to equal 16 minus 2 squared minus 1 squared, which of course is equal to 16 minus 4 minus 1, which is equal to 11. So then we're going to evaluate f at 2.1, 1.05, and that is going to give us 16 minus 2.1 squared minus 1.05 squared, which is equal to 10.4875. So those are our values of f at those points in the function. We are going to use those later when we get to evaluating our differential. So the next thing that we're going to do is we are going to differentiate f with respect to y of x and y, which is only going to involve differentiating this x squared because it is the only component of the function that contains an x. So this is going to end up being negative 2x. Then we're going to evaluate the derivative of f of y at xy. And very similarly, this is the only component of the function that contains a y. Therefore, that's the only thing we have to derivate, which will give us minus 2y. Okay, so now that we have that information, we're going to go ahead and figure out what our delta x and our delta y are, because these are things we're going to need later as well. Because as we know, this is equal to dx and dy. And of course, it's very easy to do. We're simply going to subtract one from the other. So for x, it will be 2.1 minus 2, which will equal 0.1. And we'll have 1.05 minus 1, which of course equals 0.05. So now that we have all of that information, we are going to go ahead and create our total differential dz for our function, which is going to equal f sub x at 2, 1 dx plus f sub y evaluated at 2, 1 dy. Okay, and that's pretty easy. Don't need to go ahead and do that separately. I think you can pretty easily put the 2 in here, and so you're going to get a minus 2 times 2 times our dx, which is 0.1, plus, and we're just going to put a 1 into here, so it'll be a minus 2 right here, times our dy, which is 0.05. My eraser. Okay, and so then we are going to end up with a negative 0.4 plus a negative 0.1, which of course is going to give us a negative 0.5, is the answer we get from our total differential. Now this is more of an estimate. The next step that we're going to do is going to get us a more accurate number. Okay, and what we're going to do for that is we are going to use the fact that delta z is equal to f of x naught plus delta x, comma y naught plus delta y. And then we're going to subtract that from f of x naught, y naught. So that is going to end up being f of 2 plus 0.1, 1 plus 0.05 minus f of 2, 1, which of course is f of 2.1, 1.05 minus f of 2, 1. Okay, and since we went ahead and solved for these earlier, we already have these values. So this is going to be 10.4875 minus 11, which is going to give us negative 0.5125. Now, as you can see, these numbers are super close to being the same. As a matter of fact, this is just this rounded off. So we have successfully been able to estimate the value of the function's derivative and then find a much more accurate value of it using what we learned about the total differential. Thank you so much for watching my video. I hope you were able to enjoy it, and you guys have a terrific day.